Okay, so let's explore the simplex method. All right, so the simplex method is predicated or based upon the fact that the optimal solution lies at the extreme point. If you recall from our previous notes on the graphical solution, we saw how that optimal solution arose at the extreme intersection. But in order to figure this out or utilize this fact, we need to know if we are at an extreme point. And in order to do that, we need to change our inequalities to equalities by introducing some slack variable. And as the name suggests, the slack variable tells us how much of a constrained resource is available. So it tells us if how much slack we have. So for example, we saw that in one of our resources, we had the following relationship or inequality, that 7x1 plus 11x2 must be less than or equal to 77. So now if we define a slack variable, S1, we can change this inequality into an equality by setting up the following. 7x1 plus 11x2 plus slack, so now I'm introducing some slack into my system, equals 77. Now, this shows us that it shows us some important points, and that is if the slack variable S1 is greater than 0, then we have some slack or resource availability in our system. If it is less than 0, then we have exceeded our constraint, and if it is equal to 0, then we have met our constraint. So we can go ahead and write the fully augmented system from our example that we've been using. That is, we want to maximize the profit, Z, which is equal to 150 multiplied by resource x1 plus 175 x2. And our system, 7x1 plus 11x2 plus our new slack variable, I'm going to leave some space and you'll see why shortly, equals 77. And then our second constraint, 10x1 plus 8x2 plus another variable, let's call it slack variable 2, equals 80, and we said that x1 must be, I think it was less than or equal to 9, but we add in our slack variable, so we call it slack variable 3 equal to 9, and we had x2 must be less than 6. So we want to change that into an equality by adding slack variable 4. So I hope you can see that this is actually, well, this should be quite familiar to you. And something to note that now we have m slack variables and n variables. So we have a total of m plus n, which equals to 6 variables, but we only have 4 equations. And this means that our system is now underdetermined. Okay. Now, just at this point, I'm going to redraw our graphical solution. Okay, where we had our graph, x1, x2, we had something looking like this. Okay. Now, just to recap again, we had 6 variables and 4 equations. And it turns out that the difference between the unknowns and the equations, which equals to 2, is directly proportional, or it's directly related to how we can distinguish between the feasible extreme points. So, if we look at our plot, we have the following extreme points. At our origin A, at B, at C, D, and E. So now, at A, the following 2 variables that need to be 0 in order for us to solve our equations are x1 and x2. At B, we set x2 and s2 equal to 0 in order to solve our equation. And we can carry on, C being s1 and s2, D being s1 and s4, and E x1 and s4. I hope you can see that. If you can't, I suggest you relook at our equations from the previous system and try and figure out what variables you would need to set to 0 at each one of these extreme points in order to find the solution or feasible solution. Okay. Now, in general, a system of m, let's write this in black again. So if we have m linear equations with n plus m unknowns, this can be solved for a basic solution by setting n non-basic variables equal to 0 and solving for m basic variables. And if that solution is greater than 0, we call it the basic feasible solution. Now, to calculate all the basic feasible solutions becomes very tedious, and we can address this with the simplex method. And we will get onto that in the next session. But just to give you an idea, if we have n plus m variables, and we said we have n non-basic and m basic variables, then the total number of simultaneous equations required is equal to n plus m factorial divided by n factorial m factorial. So have a look for yourself. If you've got 6 unknowns and 4 equations, how many solutions are possible, and of this, how many are feasible?